Hi guys. Okay, yay, we have made it to Unit 7, which is one of the shorter units that we're going to cover, but probably the most important as far as general chemistry concepts go. And it is all about the mole. And the mole is a unit that is used often in chemistry because it makes the math easier. And it is basically a conversion factor that was used to substitute a much smaller number for a very large number that could make counting molecules or calculating numbers of molecules associated to other units much easier. So a guy named Amadeo Avogadro was really good at math and really good at chemistry and physics and all those things. And he calculated that a mole, which was just a shortened version of molecule, is a number that is equal to the number of atoms in for any different type of element on the periodic table. And so he based all of this on the number of carbon atoms that are in 12 grams of carbon. 12 grams is the molar mass of carbon from the periodic table, and so he calculated how many molecules could actually be in that amount of grams. And he came up with a number 6.02 times 10 to the 23rd. And so that's that big number that is listed there at the bottom of the screen. Yikes. So obviously it is much easier to multiply something by 1 than by that number. And so this number is known as Avogadro's number. It is one of those things that has been figured out and has never been wrong. And so it is the basis for lots of different calculations. Okay, so here is the conversion factor. This is what I will have you or have had you write on your periodic tables. And when we are converting from moles to grams or molecules to liters or whatever it is, this is what you will use. And so once Avogadro figured out this first little part, so this over here, then they realized, they based it on carbon, but they realized that it would apply to any element as long as you knew its molar mass, which conveniently enough is what you can get from the periodic table. So right here, this go to the periodic table to get molar mass. The reason that that is a blank is because it's going to be different for every element. So if you know the molar mass, then you can do a mole to gram conversion or vice versa. And it's really important to be able to do that because that's what we measure things in. That's what our scales are set to. And so we don't have anything that measures molecules, but we definitely can measure grams. And then the last unit, the last quantity that we can find is in liters. They determined that 22.4 liters is the volume that 1 mole of a gas would fill at standard temperature and pressure. And essentially what they did is they took 1 mole of a substance that is normally a gas and condensed it down, or you condensed it and then had the right mass of that, and then put it in a space and let everything warm up, and the pressure became normalized, and it filled approximately 22.4 liters. The standard temperature and pressure is like room temperature and sea level pressure. Okay, oops. Here are a couple of examples. I'm going to show you the setups. I don't actually have, oh, I do too. I'll show you the answers and how to set up this first one. And of course, if you're in class, then we will work them there. But in case you're not, this is what we will do. So it's going to be just like a factor label problem like we did early in the year. And so you would have your given, which is 93.7 liters. The CO2 is not super important in this one, but I just want to include it just so you see the units, because I always want you to put units. And then I want to convert it to moles. So moles are what will go on top. Then because we have liters CO2 on the given, then I know I want liters CO2 down on the bottom. That's so that those units will cancel out. Okay, so from the equation on the page before, we said that 1 mole is equal to 22.4 liters. Okay. So when you work these problems, it is multiply across the top and divide by the bottom. So it would be 93.7, hang on, let me get my calculator here. Okay, so 93.7 times 1, which is of course 93.7, divided by 22.4. And you should get something like 4.18 moles. All right, so the next one I'll show you, I'll write the setup and we'll see if you can get it if you're working them on your own. So start with my given again, 4.78 times 10 to the 22nd. MLC is the common abbreviation for molecules, just so you know. And then our little conversion factor. Yikes, my line's not really straight. Okay, so I want grams. I'm talking about grams of SO2. So from the equation on the page before, grams was blank. That's because the G in grams means you have to go to the periodic table, add up the molar masses, and put it in there. So S has a molar mass, if we round to whole numbers, has a molar mass of 32. Oxygen has 16. I have 2 oxygens, so that's 32 plus 16 plus 16, which should give you 64. And then on the bottom, I have molecules. So over here, I'm going to put molecules. And then the number that goes with molecules. The long word gets the long number. So 6.02 times 10 to the 23rd. Oh, my 2 disappeared. Times 10 to the 23rd. Sorry, that's not super clear. And so when you punch this into your calculator, use your scientific notation button, 4.78, and then like the little EE or the EXP, 22 times 64 divided by the 6.02 times 10 to the 23rd. All right, so you work that one and we'll check it in class. Okay, so now percent composition. This is kind of the next problem that will lead us into another problem that will involve moles. But percent composition is the percent, and I have a typo, so sorry, by mass of each element in a compound. And so first off, you're going to find the molar mass, which just means add up the mass numbers for the compound from the periodic table. And then you divide the individual element's mass times the molar mass of the compound times 100, and that gives you the percent of element. This is just a percent problem. You have worked problems like this for a long time. And so now it's just applied to 2 elements. Okay, so here is an example. Find the percent by mass of sodium in sodium sulfate. So here's the formula for sodium sulfate. So first off, when you're doing the molar mass, you add everything up. So sodium is 23. There are 2 of them, so I have 23 plus 23. S is 32, and then oxygen is 16, and I have 4 of them. So I have that whole long list. And so you would add all of those up, and when you divide out, so you're going to do your setup, something over something times 100. The bottom number is what you get when you add everything up for those molar masses. So I think I know the answer, but I'd hate to tell you wrong. So let me do this real quick. So you get 142. So that goes here. So 142. And then if we're talking about the molar mass of sodium, so we just want sodium, then I am going to use sodium. So I've got 2 sodiums, so I add those together. And so I would have 46 divided by 142 times 100. And you're going to get 32.4%. So of that compound, about 34% of it is sodium. Okay, so now uses of percent composition. The first one is if you want to find the mass of an element in a container. So it's basically like the problem we just did, but you work it a little bit backwards. And so you change the percent to a decimal, then you multiply, use that decimal and multiply it by the total mass. That will always be given in the problem. So a fertilizer is 20% nitrogen by mass. How many grams of nitrogen are in 300 grams of fertilizer? So we have 20%. When I change that to a decimal, it becomes 0.2. Okay, so that's 20% changed to a decimal. And then I multiply it by 300 grams because that's my total. So when you multiply that, you will get 60 grams of nitrogen. So if in my hand I have 300 grams of fertilizer, if I could separate it all out, pick out all of the individual elements, when I weighed out the nitrogen pile that I had picked out, it would be 60 grams. Okay, second use of percent composition is to find the empirical formula. And so the empirical formula is the reduced version of an element, or excuse me, of a compound. And by reduced, I mean that it's like a fraction. If your subscripts are numbers that are divisible by the same number, then you can divide it out and make them smaller. So the empirical formula of C2H6, 2 and 6 are both divisible by 2. So that would become CH3. Remember, there's a little understood 1 after that C. And then our example, what is the empirical formula of C6H12O6? All of those numbers are divisible by 6. Evenly divisible. You want to get whole numbers here. Evenly divisible, so you'd have CH2O. Okay. So now, the next one, this is really what it's more useful for, I think, as far as chemistry goes, and that is calculating the empirical formula. And you have to have some information. You have to have the mass, or you have to have the percent of the elements in the compound, and then you run through some steps. So step 1, if you are given a percent, you remove the percent sign and basically like erase it and put a G there. You change it to grams. We can do this because we make this assumption that you have 100 grams of that compound. Okay, so if it says it's 20% sodium out of 100 grams, that means I have 20 grams of sodium. So anyway, so you do that, and so there's no real problem there. You just change the signs. Second sign is where the moles come back in, and you convert the grams to moles. And so a little factor label problem, you start with your given. So there is your given, the sample grams. You're converting to mole, and then that molar mass comes from the periodic table. All right, so then however many elements you have in your compound, you do a gram to mole conversion. Then you look at the answers that you got for your number of moles. You pick out the smallest, and you divide each number of moles by that smallest number. For our purposes, I'll mostly give you examples where they meet number 4. If the numbers divide out evenly, so your division answers are whole numbers, then these will be the subscripts for the elements in the compound. If the numbers have decimals, like if they have a 0.5, then you can multiply all of the numbers by 2 and then get whole numbers. If you have like a 0.99, that's going to round up to a whole number. Or if you have a 0.1, it will round down to a whole number. So there are different things you can multiply. For the most part, because I just want you to know the concept, it'll either be evenly divisible or you'll see a 0.5. Okay, so here is our example, and I know this looks kind of weird. I put it all on one page so I could do all the steps on one page. If you're writing the notes, by all means feel free to just kind of list it, one after the other down the page. Okay, so the question is, what is the empirical formula of a compound if it contains 40% carbon, 6.67% hydrogen, 53.3% oxygen? Okay, so first step, this one's already done, because basically all you do is get rid of the percents and put grams. Okay, so everything just gets changed to grams. Okay, so that's what's happening here. So that's it. Nothing big. Then the second step is where you take each of those grams and you convert them into moles. And so 40 grams of carbon, you're going to multiply that by the 1 mole. And then that blank down there, remember the blank for the grams means you go to the periodic table and you fill that in. So for carbon, it is 12. For hydrogen, it is 1, and for oxygen, it will be whole number 16. So when you do the first one, so you have 40 times 1 divided by 12, you're going to get 3.33. Okay, then for the next one, 6.67 times 1 divided by 1 is 6.67. And then for the last one, 53.3 divided by 16 also gives us 3.33. Okay, so now I have my mole numbers. So the third step is where you pick the smallest mole number and you divide everything by that. So I have two numbers that are the smallest. They're the same number. So that's 3.33. So for the first one, 3.33 divided by 3.33 equals 1. The next one, 6.67 divided by 3.33. Pretty sure it is one of those that we round. So let me plug this in real quick so I don't confuse anybody too much. Okay, oh, so now you get 2.003. So we'll say 2.00, so a whole number. And then the last one, 3.33 over 3.33. That's 1 again. So those numbers, because they're all whole numbers, give me my subscripts. So I have 1 C, I have 2 H's, and I have 1 O. So I can calculate the empirical formula. Okay, so now molecular formula. This is where you go backwards. So now we just got it in the reduced form, so now we want the unreduced form. So there are steps to this one, of course, and I love the steps because remember, if you follow the steps, you're going to get it. So first thing you're going to do is find the empirical formula like we just did from the given information. And then you're going to find the molar mass of the empirical formula compound. So you would add up from the periodic table the mass of each element in the compound. And then you would use this little ratio. You're going to be given a mass in the problem. And then you will divide it by the empirical formula mass, and you will get a whole number. 3, 5, 2, whatever it is. They're not going to be like huge, but you'll get a whole number. And you're going to multiply all the numbers of the empirical formula, that's what EF stands for there, by the molecular formula, okay? Or by the molecular formula, good grief, ratio. So whatever answer you get there, that's what you're going to multiply them by. Okay, so here we go. This should look familiar to you. It's the same example that we just used. A compound contains 40% carbon, 6.67% hydrogen, and 53.3% oxygen. What is the compound's empirical formula and the molecular formula? So if you refer back to the example problem that we did just a few slides ago, we have already calculated that the empirical formula is CH2O. All right, so now we've done that. Then our second step is to find the molar mass of CH2O. So molar mass is 12 plus 1 plus 1 plus 16. Okay, so 1 carbon, 2 hydrogens, and oxygen. Sorry. So 12 plus 1 gives you 30. So we've got 30. So then to get our ratio, we take the mass, the ratio, I'm having troubles today, take our given mass, 90 divided by our empirical formula, 30, and that equals 3. And then I'm going to multiply all of the subscripts in that by 3 to find my molecular formula of C3H6O3. So in nature, most things are going to be the actual molecular formula. They are bigger compounds usually than just the ionics and the simple salts and those kinds of things. So very often they're not naturally the reduced form. And so that's what the molecular formula will give you. Whew, okay, so I know I flew through that really fast. So feel free, of course, to ask me questions as you go back through this and listen to the examples and those kinds of things. Follow along and make sure you know where everything is coming from. All right, Thanks, guys. Bye.